Hello, and thank you for joining me for this session on sensor technologies. My name is Rob Webb. I am a product specialist with IDS, and over the next 20 minutes, I'd like to talk to you about the latest trends and advances in sensor technologies and how these can benefit the user. And for balance, I'd also like to briefly discuss instances for when sensor-based features may not necessarily offer the best solution. And then finally, I'll look at what we can expect in the future. I should preface this information with a note that I'll only scratch the surface of some of these technologies, and a lot of the information is borrowed from my colleague Thomas Metzger, who is our technical team lead for sensors and optics at IDS. And he recently provided a talk on our Vision channel, and this provides more depth on many of the topics. So I encourage you to take a look at this at a later date, and also take the opportunity to browse and view a number of other interesting and informative talks that are available there. Those not familiar with IDS, we are a family-owned machine vision camera manufacturer based in Germany, and we have over 20 years experience in USB and GIGI cameras for almost any machine vision task. Our product portfolio includes compact industrial cameras, board-level OEM cameras, 3D stereo imaging cameras, a new complete end-to-end AI processing camera, as well as some semi and fully custom offerings. As a manufacturer, we are developing new cameras all the time, so are constantly tracking and assessing these sensor trends to bring the latest advances to our customers. The number one trend is increased resolution and the subsequent reduction in pixel size. Smaller and smaller pixels means that cameras can offer more resolution, more megapixels, and this is without affecting the optical format. This is the case for smartphones, for CCTV cameras, DSLR cameras, and for machine vision. Samsung have recently announced production of a sensor with 0.64 micron pixels, and OmniVision is working on a 0.61 micron pixel sensor. It's easy to overlook just how small this is, but 600 nanometers is the same as a wavelength of red light, or half an anthrax bacterium. These sensors will be for the smartphone market, and machine vision sensors tend to lag behind, but already there are sensors with less complex rolling shutters boasting 1 micron pixels and 2.5 micron pixels on global shutter sensors in machine vision sensor cameras. Broadly speaking, smaller pixels means less imaging performance. Two common measures of imaging performance are quantum efficiency, which is the probability of the conversion of a photon to electron, which then becomes the gray level in our image, and full well capacity. This is the number of photons we need to collect in a pixel to reach saturation. And this affects the dynamic range and the signal to noise ratio, and ultimately determines the ability to detect changes in gray level or intensity. And both of these measures can be negatively affected by a reduction in pixel size. The demand for resolution is understandable, especially in the consumer market, but whether you actually need these or not is another matter, but big numbers sell devices. Reducing the size of the pixel actually means that the fabrication process is more complex and more expensive. So then you might ask why sensor manufacturers would want to accept this increase in costs. Well, it comes down to yield, which ultimately keeps the price per sensor lower. Imaging sensors are manufactured on wafers, and in the example here, each square on the wafer is an image sensor or die. During the production process, contaminants like dust or other process failures can cause and do cause defects. With larger sensors, you might have a scenario where 18 out of 28 sensors are affected, producing a rather disappointing yield of 35.7%. And as we decrease the size of each die, keeping the same number of pixels per sensor, we can see that for the same defects, whilst the number of defective sensors increases, the percentage yield increases massively. And it's this that motivates sensor manufacturers to implement more costly manufacturing processes. Higher yield equals higher income from higher volumes of lower cost sensors. Now, I mentioned that the smaller pixels tend to lead to less performance. So how have sensor manufacturers mitigated this? There are a number of counteractions and improvements implemented to improve the light capturing ability of a sensor. Some of these are likely to be familiar for anyone who has been using machine vision cameras before. Micro lenses over each pixel ensures that more of the light is redirected to the sensitive area, and this can make a big difference to the quantum efficiency of the sensor. The micro lenses also ensure that the light destined for one pixel doesn't end up being detected by an adjacent pixel. This is something we call crosstalk. And finally, the lenses also provide a better angular acceptance, which ensures lower vignetting with shorter focal length lenses. But really, micro lenses are old news. The majority of machine vision sensors to date have been what is called front side illuminated. We can look back at our simplified diagram before and note how the photosensitive area is behind a bunch of readout wiring for each pixel. And despite the best efforts of the micro lenses, photons are still absorbed and reflected by these wires, affecting our quantum efficiency. Our friends in the smartphone and CCTV worlds have had the jump on us again here, as they adopted backside illuminated sensors over a decade ago. Backside illumination takes the image sensor and flips it so that all the readout wiring is behind the pixel, and photons have this uninhibited path to the photodiode. If we compare the performance of an older front-side illuminated sensor with the same pixel size as a newer backside illuminated sensor, I'll not name and shame the older sensor out of respect. It was very good when it was first released. But we see that we get a marked increase in performance in quantum efficiency, in full well capacity, and consequently in signal to noise and dynamic range. These measurements are taken using the EMVA 1288 standard for unambiguous sensor comparison. And if we also compare to a current front side illuminated sensor with larger pixels, with some improvements in the read noise, the performance is equivalent despite the smaller pixel area. A few three-letter acronyms to introduce now: DTIs, VTGs, and buried CFAs. DTIs, or deep trench isolations, are essentially barriers between pixels to limit crosstalk between adjacent pixels, and therefore increasing the sensor level MTF. There's another one. MTF is modular transfer function and is, in short, a measure of how well a sensor or a lens can maintain the original contrast of a scene by getting the right light into the right pixel. And a higher MTF means better image clarity. With the DTIs limiting crosstalk, the size of the photodiode can also be increased. This would ordinarily increase crosstalk. And this increase means we have a higher well capacity, so our dynamic range is improved for the smaller pixels. Vertical transfer gates, VTGs, is a way to more efficiently read out the electrons from larger pixels so that fewer electrons remain. This is a phenomenon called image lag. And then finally, buried CFAs are color filter arrays. And this is a way to minimize crosstalk between the color filters on each pixel where the deep trench isolations don't extend. One further innovation is the use of scattered surfaces. Once the photon is safely through the microlens, a jagged surface scatters the photons and the path traveled within the silicon is increased. And this results in a higher probability of conversion to an electron. This effect in particular enhances the detection of longer wavelengths, especially near infrared. And it's a technique that's been adopted from solar cell technology. Backside illumination therefore mitigates some of the negative effects of smaller pixels and offers improved performance compared to equivalent front-side illuminated sensors. And coupled with the pixel level features for smaller pixels, this can mean with our higher resolution sensors, there are cost savings since fewer cameras are required for an application. Better resolution offers improved processing performance, or again, by reducing the number of cameras, the system complexity is reduced. And there may also be a reduction in lens costs, maybe. Another recent innovation is stacked sensors. With the Sony Pregius S range, this came hand in hand with backside illumination, but other sensor manufacturers are also offering stacked sensors. Where most sensor packages have a border with the circuitry logic around the outside, the stacked structure means the physical size of the sensor is significantly smaller. Consider the percentage of actual pixel area to other bits on the second generation Pregius sensor on the left, compared to the Pregius S on the right. What this ultimately means is that along with the smaller sensor format, we as camera manufacturers can accommodate higher resolution sensors on smaller cameras, especially important for space-restricted applications. Furthermore, the stacked structure also increases the scope of possibility for more sensor-based processing features. Speaking of which, there are a number of interesting features offered by some of the latest sensors, which traditionally have been performed by on-camera FPGAs or on the host PC in software. Features such as self-triggering, where a smaller region of interest is set on the sensor and then monitored. And when the scene changes in that region, it automatically triggers the acquisition of a full image. Very useful if you need to manage the data bandwidth from a camera or network of cameras, since you only send data when something notable happens. And we will see another interesting approach to this in the final section. Internal high dynamic range processing is possible. A dual analog to digital converter on the sensor allows low gain and high gain images to be taken simultaneously and then combined on the sensor to produce a high dynamic range image. This is normally an FPGA-based or host-based pixel operation that takes up valuable resource or compute power. These sensor-based features can free up processing resource elsewhere, reduce the processing platform requirements, or even realize applications that previously were not possible, either because previously potential costs were too high, or simply because the technology didn't permit it. It would be remiss not to mention increasing frame rate as a general trend. High-speed sensors have been available for many, many years, but as sensor readout methods improve, it has led to faster frame rates without compromising on resolution or sensor performance. The latest Sony Pregius S sensors are offering 25 megapixel resolutions at up to 106 frames per second in 8-bit mode, and the latest Onsemi X series offers up to 45 megapixels at 40 frames per second, and that's 12-bit data. This, of course, also puts a strain on the data interface to the processing platform and the processor operating on those pixels. But putting that aside, more frames per second means more products can be inspected, so production throughput can increase, or 100% inspection can be achieved. And higher frame rate can also mean improved accuracy on analysis of images for whatever purpose that might be. So these are the main trends in the current crop of sensors, and the potential benefits are clear. But whilst these new trends offer better performance and new features, there are still many applications we see that don't require high resolution or high speed or high feature sets, and are more focused on optimization of functionality, performance, or costs. There's also the consideration that sensor-based features may limit the scope of what a camera can do, and the majority of current machine vision cameras benefit from having an FPGA on board to provide additional processing, such as subsampling or binning, Bayer pattern processing, shading correction, or image sharpening, to name but a few. Plus, an FPGA also gives the opportunity for camera manufacturers to offer more niche custom processing where the application demands. In other situations, a simple camera that delivers a good quality image has minimal on-camera processing, meaning there's no need for the expense of an FPGA, lower power requirements, and has a reliable data interface and wide software support with rich software feature sets, can and does solve many applications. And the economies of scale are clear when you can produce a higher volume of products with lower cost materials. Taking a look now at the future of sensors, we will see some new technologies and approaches, some continuation of existing trends, and some existing technologies made more commercially viable. On the continuation of trends, we will no doubt see the advances that are being made in smartphone cameras with even higher resolution, smaller pixels and smaller sensors adopted in the machine vision world. Although this brings new challenges since we are often far more interested in real pixel level information, and pixels that are the same size as a wavelength of visible light presents a challenge, and lens manufacturers also need to provide optics that can support such tiny pixels. It will be interesting to see wider adoption of existing imaging techniques in the machine vision market. Last year, Sony announced a 1.3 megapixel shortwave IR sensor with 5 micron pixels that, with spectral sensitivity from 400 to 1800 nanometers, can address a wide number of industrial and non-industrial applications. And in recent years, we have seen sensors with pixel level filters providing a Bayer pattern type approach for visible wavelengths, which provides a more compact solution. And we're likely to see improvements and wider adoption of this sensor technology, especially for applications in food and agriculture, and with other specific filtering in automotive applications to enhance intelligent traffic systems and autonomous driving. One of the consistent challenges for machine vision cameras, and I've mentioned it here already, has been the managing of data bandwidth, especially in multi-camera applications or in processor limited systems. From one image to the next, every single pixel must be exposed, read out, and then transferred to the processing platform. And this can mean a significant bottleneck. In applications where you might analyze motion of an object, you are first transferring a large proportion of data that is temporarily the same. And secondly, the time between exposures mean you lose some potential information as an object moves through the scene. And we can take the example here of our big cat. The self-triggering on some of the newer Sony Pregius sensors may address this to some extent, but event-based imaging addresses both of these limitations by sending events only for pixels that have changed in the scene. And because of a faster readout, the time between events is minimized, meaning more temporal variations can be detected. So now you can really optimize your golf swing. Another way to manage data bandwidth is edge processing. Rather than send the entire image, you process locally at the sensor and send just the result. And this is nothing particularly new if you are a smart camera user. However, with improved processing technology and optimized neural network models, the deployment of artificial intelligence and deep learning on edge processors has recently come to the fore. IDS provides an end-to-end solution for deploying camera-based AI solutions with our NXT Ocean products. You can see our Vision channel for some talks on this product range. Last year, Sony announced a new sensor equipped with AI processing functionality, where the AI model is loaded to the embedded memory on the image sensor itself, and then can be configured to output just metadata or the original image. And we're only really at the very start of what is to come with deep learning possibilities, especially when you combine it with some of the sensor techniques previously mentioned. So to summarize, the sensor market stating the obvious, has changed a lot and will continue to change and evolve in the coming years. And there are lots of exciting developments, some that are niche and others that will serve the broader machine vision world. The consumer market continues to drive the main trends here. But still, many applications can benefit from more standard cameras. A high-spec sensor does not always mean a camera will be a perfect fit. So it's important still to seek out the best solution for your application. Whilst IDS may not implement everything that I've presented today, we're always keen to discuss your applications. So please do get in touch about any projects or special requirements, and we will be very happy to help. Thanks for watching.